This lecture is about how we train these neural networks, and the agenda will be first we will just go over the basics, which will be required actually to talk about the whole process. And the basics I think we have already covered. It's just a recap. Then we will talk about optimization, and this is like the main step, which is the training process. And then we'll briefly talk about backpropagation, which is again a step which is used while training these networks. And then we'll try to cover some of the practical aspects when you do programming assignments. I think it will be very useful. And finally, I will show you like some CNN variants and like some motivations why those CNNs were designed to wrap up this lecture. All right, so let's begin with the first segment. Now, let's first try to understand the concept of network parameters. We have been talking about this a lot, but let's make sure that everyone understands this pretty clearly. So in a neural network or in a convolutional neural network, you will have input. Okay, so there is a distinction between data and parameters. Both are actually storing some values, some numbers. Okay, so in that sense, they are like similar things. But data is something which depends upon your input sample. Okay, so what value like you will have in this activation will be highly dependent upon what image you have used as your input. If let's say this is like activation map in some of the after some of the intermediate layers. Okay, so that's one thing. Then there is one more thing which is called parameter or these kernels, which will also control what these values will be, right? But these values will not change by changing your input sample. Okay, so if you have a kernel which has certain values, for example, this 3x3x3 filter, it will have 27 different values. Those values are actually representing your network. They don't represent your data or your input images. Okay, so they are part of your network. And these are called parameters, and these will be learned when we train the network. Okay, so for convolutional neural networks, these kernels will be learned. For example, in this case, these 27 different values. So how it works is we initialize the weights randomly, which means when you start your training, you will randomly select like some values for these kernels. And as you train your model, these values will be changed. Okay, so these are the parameters. And in neural network or fully connected layers, your neurons will contain like the values or the activations. But when you're trying to connect two different neurons, you will need some weights to compute those linear combinations, right? So those weights are the parameters. And again, those weights at the beginning, you will initialize randomly. But as you train your model, those weights will be changed. Okay, so these volumes are, again, as I said, they depend on the input data and also on the kernels, but these are not part of your network. This is just data flowing into your network. Now, if you look at this example here, this is the input image and the kernel which we are striding, right? The red kernel or the green kernel, that's the filter. So those are the parameters. Those are the weights which will be learned. So we'll try to learn this filter. And again, this we just saw in the previous lecture. These are not weights. All these are just activations. And this is kind of a data flowing into your network. And this will vary with the input image you have. But how you obtain these activation maps using these convolution operations, those are the network parameters which we are going to learn. Okay, so a general CNN architecture, as you all know by now, you have input image, you have certain convolution layers, some subsampling layers, or some normalization layers, and your data will flow in your network. You go from feature maps to feature maps, and finally the output. And the way it works is you have your input image, and as I said, you initialize these kernels randomly. So even without training your network, you can actually have an input image, and you can still get these activation maps, and you can get some kind of prediction. But since the network was randomly initialized, it was not trained, what will happen is you will get some kind of output which will not mean anything. I mean, it will not be the right prediction, right? So then the whole idea about training is you take that prediction, whatever that is, we don't care about that, and then try to compare that with the actual ground truth, okay, the value which the network should have predicted. And then we try to say, okay, this seems like a bad prediction, or this seems like a pretty close, but it needs to be improved, right? So we can kind of estimate like how good the network's prediction is. And what we do is we design like a loss function, which tells you how good your network's prediction is. And then based on that estimation, it will just give you one value, how good your network is. And that value will be used to update all the network weights. So there's like a back propagation here, which goes backwards. And there is a feed forward operation, which happens when you start with the image, apply the convolution, get this feature map. So that's called like the feed forward, going forward, getting the prediction. Okay, so there are two operations when you train your model. We'll talk about that in more detail later. So the basic training operation, I think, again, we have covered this in the past. You have your training data. So you don't train just on single image. You train on lot of images. And that's one of the limitation of deep learning. You require a lot of data. Okay? So you have all these images and you can extract features, or you can use like CNN to extract features. And then you need these labels, which are called ground truths, right? So then again, for all these samples, you try to make predictions, and then you make use of these labels to say how good the network is doing. If it's doing bad, you will penalize the network. You will say, okay, the weights are not good, improve the weights. So that act, when you say that improve the weights, that is called network training. Okay? So during training, all you're doing is you're trying to change the weights of those kernels. That is called network training. The next segment is the optimization process. And this is like the core of network training. And I think the important part you need to understand is the concept of loss function. As I said earlier, loss function is something which tells you how good your network or how bad your network is performing. Okay, so it is a way to tell how good the network is doing or how bad the network is doing in terms of the prediction, which again, it will, if you think about this, it will vary a lot from problem to problem. Right? So right now, we'll just focus on, let's say, classification, where we just say that, okay, this class is present or this class is not present. So it's just one number there, right? But if you think about this, that's classification. If you go to detection, the prediction will completely change. You will have that number which will say, okay, object is present or not, but then you also need to predict like the location or the bounding box. And it will get more complicated as you move to, let's say, segmentation, where for every pixel, you will have to say which object category is present. All right. So it depends on like what task you are solving. But right now we'll focus on just classification, where you just say that whether object is present or not. And again, that concept can be easily generalized to other tasks as well. Okay, so this network training is actually a kind of optimization. And what you're optimizing is you're trying to optimize the network weights so that whatever prediction your network makes, it's actually very close to the ground truth. And the idea is, let's say your loss function is defined by this formula. This big W over here, these are like all the network weights. All right. So not just one layer, one kernel. This comprises of all the weights you have in your network, which means if you have 3 different convolution layers, or in case of AlexNet, you have like 6 different convolution layers. So all the weights there, like all the kernels in first layer, second layer, third layer, so on and so forth. Right? So this W represents all those weights. Then these weights will be input to your loss function. And what's happening here is you will need a ground truth. Right? So this loop is going over like all the samples you have present in your training data. And as we have discussed earlier, like in your training data, you will have a lot of samples. Let's say you have 10,000 samples. Okay, so N will be 10,000. And you will go to each image, and then you will compute loss for that image, right? So in this case, L is your loss function, then F is your network. And you know that the network takes an image as input. In this case, Xi is the image, that's the input, right? And again, these are network parameters. And these parameters are like, let's say, the current state of the network. If this is the first step, then these will be randomly initialized. Okay, so given a network, all those have a parameters which we discussed, which define the architecture of the network. you will send one image as input, you will use the weights, and that will give you the prediction. Okay, so for example, let's say it's a 1,000 weight classifier, then the network will predict 1,000 different values, and then you will pick like the most activated value, or whichever class is like being predicted at this time, right? So whichever has the highest value, you will say that, okay, this is the network's prediction. And then what you will do is you will have the ground truth. For this image, you will know that, okay, which object was present, right? So input to your loss function is the output of the network and the ground truth. And that's why we need ground truth to train your network. Then you will make some kind of comparisons. We'll talk about that, like what kind of comparisons we can make. But you can easily say that, okay, whether this prediction is good enough for this kind of ground truth, right? Whether it's close or it's a very bad prediction. So this function will give you some value, right? And let's say that's ranged from 0 to 1. So 1 means very bad prediction, 0 means very good prediction. It means you were able to predict the ground truth. So then you will average that over all the samples, all the training samples. So then essentially what's happening here is this loss function is telling you like the average loss, like how good your network is performing on this training data. If this value is 0, then you can say, okay, the network is actually very good. It didn't make any error. If the value is 1, then you say, okay, it's pretty bad. It's useless. Every time it's making a mistake. Okay. So this loss function is giving you a sense. It's just giving you one number, which determines how good your network is performing at that stage. And remember, all of this also depends on these weights. So now what we want to do is, whatever loss we got, we try to minimize that loss. So we want that loss to be 0. And to do that, we will try to modify these weights. So we want such a weights which will make this loss value equal to 0. So this is the optimization process which we'll have to perform. The next segment is the optimization process. And this is like the core of network training. So let's try to understand like how this optimization is done. So we use gradient descent, and you might have studied this algorithm in the past in some of the courses, maybe in statistics or so. But I will give you like a quick recap of how this gradient descent works. So, and again, I mean, there are a lot of other optimization algorithms you might have, maybe in numerical calculus, or you might have studied. But gradient descent is one of those which I think is very useful in network training. And it's a way to minimize the cost function. In our case, this is the cost function which you want to minimize. And these are the parameters which you can change to minimize this loss value. All right, so let's try to understand how this gradient descent works. And again, we'll just go with like a very simple example, a one-dimensional, one variable. But again, that can be easily generalized to high-dimensional space. So let's assume we have a function f which operates on value x. All right. In this case, let's say x is like just one value, which can be represented by this x-axis. And y-axis is the response of that function. Right? So for each value of x, you will get some kind of response. Okay. So if you think about this, f in this case is the network, and x is like the parameters you have. Okay. So when we try to optimize this, when we try to optimize like this function, then we want like the minimum value of this function f. Okay. Oh, sorry. So f not the network, it's the loss function which you're trying to optimize, right? Sorry about that. So this is the loss function f, and we want to minimize the value of the loss. In this case, we can see that the minimum value is at this location, right? The bell location, and it can't go like any further down. That's the minimum we can achieve. So the optimization, what it will do is it will tell you, okay, for x at this position, you will get the minimum value. So when we perform the optimization, we are trying to estimate the value of x. So if you map this analogy, if you map this with like the network training, and f is a loss function and x is like your weights, in that case, you will have similar kind of curve, right? For different parameters, you will get different values. It will be a function. And what we want is, we want to find the parameters of the network. So we want such a parameters where the value is minimum. Okay. So how we can do that? So as I said, we randomly initialize the network weights. In this case, let's say X is our weights. We randomly initialize, let's say we get at A1. All right. And that will give you a loss value of something like at this point. Now we know that this is the loss. By looking at this curve, I can say that I want to go towards this direction, right? Then I will be able to move this parameter towards the right. So what we do is we just find derivative at this location. And you know that derivative just gives you the slope of the curve. So if you compute the derivative, it will be something like this. And in this case, you can see that the slope is actually in the opposite direction, right? So it will have a negative value. Okay, so you can see here that it's 1D function, we can call it a derivative. But if it's like multinomial function, we'll have to compute like a Jacobian, or you can say like higher order derivative, right? So we'll have to compute partial order derivative for like different dimensions. But don't worry about that right now. Let's just assume that it's a one-dimensional function. We can find the derivative, which represents a slope. In high dimensional as well, it's like kind of slope of the curve. So if we have the slope, then we know like the direction, right? It's negative. Then what we can do is we can actually follow the direction of the slope. Okay, so if we follow that, then we can move like one step ahead. So this is like the increment we want to take. Now look carefully. First of all, this is again like some kind of hyperparameter, so don't worry about this. So we want to go from A1 to A2. A1 is the original location, and we compute the derivative of the function, right? And this gamma over here, it's again a parameter, and it's called learning rate. And learning rate, again, it's a hyperparameter. When you train your network, you will work on that a lot. So let's try to understand what that learning rate is. So that learning rate is just like how big your steps should be. Okay, so if you focus on this part, which is like a derivative of this function, so as I said, this is going to be a negative value because the slope is negative, right? So if it's negative, there is a minus sign over here, which makes it positive. And gamma is like a parameter, it will always be positive. Then what you're doing is you're actually adding this amount of value to A1, right? Because negative will cancel negative. So if you add something to A1, in which direction you will go? You will go in the right direction, right? Towards right, because you're adding something to A1. And how much you're adding? That is controlled by two things: the gradient, what is the slope over here, and the second is this gamma parameter, the learning rate. So these two control like how fast you move towards the right, or how big your step will be. Okay, so if you can compute the derivative, you can actually move in this direction. And once you are at A2, you can again repeat the process. Compute the derivative, and again, it's like a negative slope, but this time like the value of the slope is actually reducing, right? Because earlier it was like more slant, then it's going down. So then again, you're using the same learning rate, you will move to A3, and you can keep doing that. And what will happen, you can see like as you're going close to this point, your slope is actually getting lower and lower, or the derivative is going like lower and lower. And at this point, when you try to compute the derivative, it's completely going to be a horizontal line, which means the derivative is 0. So if your derivative is 0, then the second term is going to be 0, which means your value will not change. Therefore, when you reach a point when your value is actually not changing, it means you are kind of in the target location. In this case, it's the minima here. And that's what we want. So we wanted to find this value, right? A star. And that's how gradient descent help you like find this value. And again, this is one dimensional, but you can easily generalize this to high dimensional space as well. So that's exactly how your network training works when you try to use a gradient descent. But things are not that simple. Okay, so I will cover like some of those aspects why it's not simple. But as I said, like gradient descent, it's used for like optimization of functions. Now, if it's a convex function, okay, convex function is something which will have only one minima. Okay, so this is a convex function. Then you can use gradient descent and you will definitely find that minima. But your loss function will never be a convex function, right? It's going to be a very complicated function. It's always be non-convex, something like this, which means that you won't have like just one minima, you will have a lot of minimas. And then the goal is when you optimize your network, you're just trying to find local minima. Okay, if you're in this neighborhood, you are interested in this. If you are in this neighborhood, you are interested in this. And again, there could be like a lot of other local minimas. And that's one of the issues like when you train your network. And that's the reason when you train your network at multiple times, you will get different results. The reason is you are initializing your weights randomly, right? So it could be like when you initialize your weights, you start from this location. In that case, you will end up at this location. But another time you might be initializing with this point. In that case, you might end up at this location. Okay, so this will give you like two different networks when you try to optimize it. Now, let's see how you train your CNNs with this simple gradient descent algorithm. So you have n training examples, right? Xi is your image, Y is the label. And let's say Fx is your feed-forward network, which takes image as input and it will make some kind of prediction, which should resemble this label. And then you need some kind of loss function, which will again take like the parameters of the network, theta over here, and it will take the image and also the label. All right. So with all this, all these set of information, what this loss function will do, it will tell you how good your network is doing, right? As we discussed earlier, it will just give you one number, and you will use that one number to actually update your weights, and the way you will update the weights is based on gradient descent. Okay, so that one number is actually nothing but some position in this curve, right? And based on that number, if you compute the derivative, you can actually move towards the minima and you can update the values of your weights. All right, so this x-axis is like your model parameters, and this is the loss function of your CNN. And at any time, like if you have certain set of weights with any input, if you try to predict the loss function or the loss value using the loss function, you will be like at any of the locations in this curve. And all you want is you want to move that point to the local minima. Okay, so let's quickly go over like some of the loss functions which can be used to estimate how good your network is doing. And the most popular one is cross entropy, and I think you will use this a lot. And I will also try to briefly explain like why it actually works. So the simple equation for cross entropy is, so you have the hat is the predicted value, and the value without a hat, that's the ground truth. Okay, so let's treat this value as 0 or 1. 0 means the object is not present, 1 means the object is present. Now, what is happening here is, let's focus on this first term first. Okay, so this is the predicted value, and this is the ground truth value. Let's consider a case where your object was present, right? And your network also said like it is present. So in this case, this is going to be 1, and this is going to be 1, right? So log 1 becomes 0, and this whole term becomes 0. And your network was actually doing a very good job because the object was present and your network said the object is present. Okay, so we are happy, the loss is 0. Now, if you look at the second term, because the ground truth is 1, this completely becomes 0. So we don't have to compute this. So if your network did the right job, your loss is 0, which means this loss function is actually doing its work, right? Now let's consider the other case when, let's say, the ground truth was 1, but the network said it's not present. Okay, so in that case, what will happen is, let's ignore this first one. let's go to this. So in this case, this will be 0, that's the predicted value, and log 1 is going to be 0. Again, you can ignore this term because if you just multiply anything with 0, that's going to be 0. Now let's come back to this one. Log 0, you know, is negative infinity, right? And this is 1, so this is going to give you negative infinity, and you have a negative sign outside, which makes this infinity. So which means that if your network is saying, okay, it was not present, but in fact it was present, this kind of loss function or cross entropy is saying, okay, the loss is infinity, which is actually good. And what you do is you compute that loss function for all the samples in your training set, and you just average that. Okay, so that's one kind of loss. You can also compute like mean squared error. This is just you do pointwise comparison. Right? You just subtract the values and you square the values and just take the mean. Okay, so that's another. So that's fine. Again, this is just telling you the difference between these two. So if the difference is like 0, these two will cancel each other, right? But if the difference is high, it will give you like some high value, which means the loss will have some non-negative value. So this is another kind of loss you use. Okay, so let's actually end it here, and we will continue the second part, differentiability, maybe in the next lecture. So today we are again we'll continue the last lecture, which was about training these neural networks or these CNNs. And we started with like the general idea how we are going to train these networks, and then we talked about the optimization algorithm, that is the stochastic gradient descent. So today we will continue on that, and the next segment will be backpropagation. And again, this is like a very I would say a broad topic. It will take a lot of time, so we'll just touch upon the basics of what backpropagation is and how it plays a role in training on networks. Now, before starting that, let's do a quick recap of what we did in the last lecture. So we were talking about optimization, and given a function, the idea is we want to find a place in this function or the response of this function where the value of this function is minimum. Okay, so that's like a high level idea of what optimization is. And in our case, this function is the loss function. All right, so the loss function which we will write, which will tell you how good your network is performing. Okay, and that we will do because we have the network's prediction and we have the ground truth. So we'll make comparisons and we'll formulate some kind of function which will say, okay, this is the loss value and how this is like how good the network is doing, this is how bad the network is doing. So that's the loss function in our scenario. And the idea is we want to find like these minima points because we want to minimize the loss. Okay, we want like the prediction of the network to be as close as the ground truth. If that's the case, the best case scenario is your loss will be 0. Okay, if your network is actually performing perfectly. So that's the high level idea. We want to minimize that function. And as we discussed, like that loss function is never going to be like a simple convex function. You might have a lot of minima there. In this case, this is again a simple one-dimensional function. It has two different minima. So one at this point and one at this point. So these are called local minimas. So usually like the loss function for neural networks, it will be very complex. So we'll have a lot of minimas and hardly there will be like a global minima. Okay. Now, the idea is we want to reach to this point, and as we discussed in the last lecture, we are going to make use of stochastic gradient descent. The idea is we initialize like our network randomly, which means that the initial prediction will be random. So with that random prediction, the loss value will be high because it will be just a random guess. All right. So in this case, let's say you initialize your network with A1. Your loss value will be something like this because that's your loss curve. And the goal is we want to move this point in this direction and reach this point. Okay, so then your loss value is actually reducing from this level to the minimum level. And your network parameters are actually going from A1 to A stop. Okay, so to go from this point to this point, this is the simple equation, which is like a single step of your gradient descent algorithm. And as we discussed last time, there are a couple of parameters here. The first is, you can look, the second term here. This is just computing the gradient. Okay, so we'll find the gradient at this point, and that will help you determine like which direction you want to go, whether you want to increase the value or you want to decrease the value. Okay, so you will use the gradient, and then you have another hyperparameter, which is gamma over here, which is the learning rate. It will control how fast you want to move in either of these directions, either left or right. Okay, so this is kind of trying to control the step size as you move from A1 to A2, A3, and A stop. And eventually, if your value is not changing, because in this case, the gradient will be almost 0. So if you're not changing, that's the stopping criteria. And you say, okay, you have reached the local minimum. And that's when your training ends. Okay, so that's the high level idea. Now, to be able to do so, you know that we were using that simple equation that was like a one step for gradient descent. So to make that one step, we need to compute the gradient. Okay, which means that whatever like functions you have like in your network, you should be able to find the derivative of those functions. Okay, so this is a very important point. So let's start from the end where you have the loss function. Okay, so first of all, you will have to find derivative of your loss function with respect to the parameters to be able to find that gradient. And to be able to do that, your loss function should be differentiable. And as you know that not all functions are differentiable. So you'll have to come up with a loss function, which is actually differentiable. Okay, not just that, as you move further down in your network, because you are going to find the gradient of your loss with respect to those parameters, which means that everything inside your network should be differentiable. And that's the only way you will be able to find those gradients, because you can't differentiate like discrete functions, right? So which means like you have activation functions in your network, they should be differentiable. You are using the convolution operation or the correlation operation when you're actually moving from layer to layer using that filtering operation, right? So that operation should be differentiable, and we know that convolution or correlation is differentiable. Okay? It's just like linear combination of those pixel values. And any other operation you are performing inside your network, for example, you are performing pooling, that should be differentiable. We know that max pooling is differentiable. And that's one of the reasons, if you remember, like when we were talking about filtering, then we came around one very interesting filter that was median filter. And we saw that it was performing pretty well. It was able to get rid of all the noise in the image, right? And the issue is that median operation is actually not differentiable. So that's one of the reasons why we can't use median filtering in our neural networks. And again, that's just one reason. In computational complexity is the other main reason. Okay, so the bottom line is, when you design your network, everything you are using inside your network, it should be differentiable. You can't just plug in like any non-differentiable function inside your network. All right. Now the question is, the gradient descent algorithm I showed you, that was a very simple function. It was dependent upon like maybe just one variable. So it's easy. You can just compute derivative of that function with respect to that variable. But the neural networks are a little more complicated, right? It's not just one variable and one function. It is actually a chain of functions. So if we start with the first layer, if you treat that as a function, then input to that function is your input image, let's say, or whatever input data point you have. And again, that's going to give you some output. So that output is again going to be input for your next layer. So if you treat like each of these layers as functions, so essentially it's like a chain of functions, right? Where output of one of the function is actually input to the next function. And eventually, like at the end, the output of the network is actually going to the loss function as input. And for loss function, you have two inputs. You have output of the network and you have the ground truth. Okay. So, but that output of the network, it's actually coming from a chain of functions. But basically, if you just combine all of that, the basic input is your image. All right. So now if you have all those functions, so to be able to compute derivative for all those variables, you will have to make use of this chain rule. And this is again coming from your high school maths. So the simple chain rule says, if you have, let's say, this function L, and you want to compute derivative of this function with respect to any variable X, and the assumption is this function actually depends on this variable X. So if you want to compute this partial derivative, what you can do is you can compute the partial derivative of this function with respect to any other variable z. Again, the function is dependent on this z, and then you can compute the partial derivative of z with respect to x. Okay, so this is the chain rule all of you must know. So this is just a recap. Now, if you try to think about the neural network, then if let's say x is like some variable inside your network, and then again that variable is connected to z, and then z is actually connected to the loss function, right? So if you want to compute the derivative of like some kind of intermediate variable or your weight in your network, so you can actually make use of this chain rule. And again, this is just one step. Of course, you can go like deeper. You can have like multiple chains here because your networks will be like very deep. Okay, but however deep it is, mean you will still be able to find this partial derivative. And this is called like a simple chain rule, and this is what is used to compute the derivatives for like a loss function with respect to all the variables in your network. Okay, and this is actually used for backpropagation. So let's first try to understand what a backpropagation is. Let's say this is a very simple neural network. Okay, and we don't know like how many layers it has. It could be just one neuron. It could be multiple layers. But whatever it is, we can represent that in form of a function. Let's say the input to this is x and y. So it will be a function. It will be a function taking x and y as input, and it's producing an output z. Okay, so this looks like maybe it could be a simple neuron, which is dependent on these two variables. Okay, so now if this z is actually being used to compute the loss function, then what you can do is you can first compute the derivative of the loss function with respect to z, which is easy because this z will be like used in the loss formulation, right? You can just use derivative equations to compute that that partial derivative. And once you have that, then the goal is to actually find partial derivative with respect to x and y for the loss function, right? So then you can simply use this chain rule. So what you can do is you can first find the derivative with respect to z, right? Which we can easily do here. And then in addition, you'll have to find the partial derivative of z with respect to x. Okay, and again, we can do that because we have this function. We know what this function is. Now the idea is, if you remember like the gradient descent algorithm, you were finding that slope, and that was a loss curve, and the x-axis was different parameters, right? So what we do, we find that derivative with respect to all the parameters we have in our network. And since we can compute that using this chain rule, we can actually take that step, whatever like that gradient step we discussed, which was making use of the learning rate and the gradient. So that step is actually performed for all the parameters. And since you have the derivatives, you know the learning rate, you can easily update the weight value. Okay, so that's actually done for all the weights in all the layers. Okay, so that's how the network is being trained, and propagating these gradients backwards, like from the loss function all the way up to the input. This process is called backpropagation. Okay, this is also called like backward pass. And the other is like the forward pass, where you have the input, you use this function to get the output value. Okay, so that's the forward pass. And to compute, you first compute the derivatives. In fact, like the backward pass is something you actually update the values of the weights using the gradients which you have computed in this step. Okay, so when you train your network, these are the two things which is happening in each step. All right, so that was just one neuron. As I said, like your networks will be like deeper and deeper, but again, you can use the same chain rule. You can just expand those, and it's just showing that because you can compute the derivative for each variable here, right? Whatever variable you have for this layer, and then again you can just keep backpropagating by computing those partial derivatives. Okay, so some simple rules like which are used. So if you are actually adding two different values, as a function, then what will happen? The gradient will distribute. So it will act as a gradient distributor, which means that whatever gradient is coming from the top, that will go equally to both the variables. If it's like if the operation is x plus y. Okay, and you can think about, because it's just a derivative, right? So if you compute derivative of x plus y, it doesn't matter. I mean, the derivative has to go to both. Okay, so that's one thing. And so if you have like the max operator, which you use for max pooling, right? So in this case, what will happen is it will act as a gradient router, because when you perform max pooling, only some of the values will be passed to the next layer, right? Others will be ignored. So if others are ignored, then it means those values are actually not influencing the output. So they're not dependent. So the gradient will be 0. So the gradient will not flow back in that direction. So whatever value was used for that max operation, gradient will just route in that direction. Okay, so it's a gradient router. And for multiplication, the gradient will switch. And again, this comes from like the simple gradient rule. If you have x times y, if you compute the partial derivative, if you compute partial, let's say you have an equation x times y, and you want to compute a derivative of L with respect to y. So then y will be just gone, right? Because it's just linear, and you will just have x. And that's why the gradient will switch. If it's y, it will go to x. And if it's coming from x, it will go to y. Okay, so just basic, don't worry too much about this. You won't have to like write any code or anything for this. These are just simple basics. Okay, so now what we do is we don't use gradient descent directly like on the whole data set, because the data set is too big. And as you know that you need like lot of images, like millions of images to train your model. So if you try to compute like the gradient or the loss function for the whole data, it will be very, very time consuming. Right. So what we do is we use like a variation of that, which is called stochastic gradient descent. And the idea is you select like a few samples from that data set, and you compute loss for those fewer samples. So that's called a mini batch, or you can say a batch. And then you perform this training. Okay. So we randomly sample like a data point. So again, this is stochastic. We just do for one point, but ideally we don't do for one point. We take like a bunch of points, which is again called not stochastic. You can say that mini batch gradient descent. All right. So, and that is also called the batch size. That's like the amount of the number of samples you're actually using to train your model. And this is one of the hyperparameter. And it actually plays a very important role, like how good your training will be. So like a very big batch size will improve your training speed, but it might not be very good for the performance. And again, if you have a very small batch size, let's say as small as 1, because you are making those updates for each sample, it's going to take a lot of time. Okay, so the idea is, so this is like a very simple training process, how it works. You first of all initialize like all the network weights randomly, and you will have some kind of learning rate. Again, it's a hyperparameter, you will choose it. And then while your loss is not like the minimum one, you will continue your training. Okay, so that's, let's say, your stopping criteria. You can have other stopping criteria as well. For example, you said, okay, we'll train the network for these many iterations, or you can say like we'll train for these many days or these many hours. You can have a lot of different variations there. So you will have some criterion to stop. Then what you will do is you will randomly shuffle your training set. Let's say you have 100,000 images. That will be a long list. You will randomly shuffle that list, and then you will start from the top. And let's say your batch size is 16. You will select like the top 16 images, and then you will feed forward those 16 images through your network. For each image, you will have some prediction. You will have the ground truth. You can compute the loss. So you will do that for all the 16 images, and you will just average that loss, right? So that's the loss for that particular mini batch, and you will use that loss value to find the gradient for all the parameters or all the weights in the network and update the weights. Okay, so if you think about this, what's happening is you are improving or you are learning your weights depending on only these 16 samples. And so that's called one iteration, because you're training your network once. Okay, so that's called like a single step of gradient descent, and you repeat that for all the samples. You will keep sampling next 16 images, next 16 images until you have used all the images in the training set. Okay, so once you're done with all the images, that's called one epoch. Okay, so that's again a term you should know. So one epoch is something when your network has actually seen all the samples in your training set. All right, and then again you repeat. You will shuffle again those images and keep repeating this process. And usually you train for like multiple epochs, and you will, as you are training those on those images again and again, your network will make better predictions because those weights are actually going towards the minimum. Okay, so that's like a high level idea of how the network training works. So this is called like one epoch when, as I said, your network has seen all the images in your training set. Let's talk about like some of the practical aspects when you train your neural networks. So we'll talk about like different concepts which you should be aware of. So as we discussed, like you will use stochastic gradient descent, and what's going to happen is, since you're training on like a mini batch, so whatever decision you make, like, or whatever updates you have taken, like using those samples, it might not lead to like a local minima, right? It might not always reduce the loss function because that decision was not based on all the samples, right? It was based on only those few samples. So it might go in any direction. So when you actually train your network and you try to plot your loss values, so let me try to explain this curve over here, and you'll have to do this a lot when you train your networks. The x-axis is the iteration, okay, starting from zero when you initialize the network. As you move towards the right, it's showing you like iterations, and if it's like 500 iterations per epoch, then at 500 it's like your one epoch, right? But that's fine. We will use like both the terms to plot this. You can use epochs as well. You can use iterations as well. Iterations is actually better because that gives you like fine-grained visualization. So that's x-axis. Y-axis is the loss value. Okay, so what's your loss? And we want to minimize the loss. And as you initialize randomly, you will have like a very high amount of loss at the beginning. So ignore like this negative sign. It's just like the loss value you have, and you can have different loss functions, right? So the values will depend on that. So you will start with a very high loss, and as you move towards the right, you train your network, your loss value should reduce. That's what you're aiming for, right? That's how you are taking like those mini steps for each parameter. So your loss should ideally go down. But as I said, you're not training your network like on all the images at once. You are taking like a mini batch at once. So it could be your loss is actually not always going down if you try to validate that on the testing samples or the validation samples. So you will see something like this. So this is like more realistic. You can see it's going down, then again going up. Okay, so it will have like some kind of stochasticity there, but eventually you can look at the overall trend. It's actually reducing. Okay, and then it's kind of a stable here. So this is like a very natural looking loss curve, which you will have to analyze when you train your neural networks. Okay, but still I think it will converge over time. That's what I said. If you try to visualize this, the same thing in like a 2D space, and this is your local minima, and this you can treat as like, it's not visible like in the flat surface, but think of this as like a bowl. Okay, a curve in 2 dimension. Now if you think about that, like this is like a high point when your loss is high, and as you're moving towards the center, you're actually going down. Now if this is your starting point, your end goal is to reach this point, and of course the best way will be you just jump there, which is actually not possible. And that's why what we do is we take like these tiny steps, and each of this step is actually going in that direction. Okay, so how big these steps will be, that will be controlled by the learning rate. If the learning rate is too high, you will make like bigger steps. If your learning rate is very small, you will take like very small steps. Okay, and both are not good. So you need like a ideal learning rate so that you do reach that minimum point, and you reach on time. Okay, so ideally what happens is it will be like a zigzag. It won't be like the straight direction. You might go in different directions, but eventually you will reach this point. Okay, so what we can do is, this is another term which you should be familiar with. This is called momentum. And if you think about this, momentum is actually taking into account what was the direction in the previous step. Okay, it's not just looking at the current step, also the previous step. And that is helping because the previous step will tell you, okay, where it was going in the previous step, then you know the current direction. So you will take both into account to make decision for this step. So it's called momentum because you are considering the past. And if you will keep doing that, then eventually when you're making a decision at any point of time, you're actually considering the information from all the previous steps, right? Because in the previous step, you consider the previous, and in the previous, so it's a chain. Okay, so that helps because in that sense, it won't be like a zigzag. It will be like a smooth transition as you go from this point to this point. Okay, so it's kind of, so this is like your normal gradient step when you are not using momentum. This is your current, this is your updated value for weight. This is the weight value in the previous step. This is the learning rate, and that's the gradient. Okay. In momentum, what you will do is you will have like additional parameter, let's say alpha, which tells you like how much of the information you should use from the previous step. Okay, so this partial derivative, you can see like this is partial derivative or the direction from the previous step. This is t minus 1 here, and you weight that with alpha. And then again, this is the derivative, same thing for the current location, right? So then you will make this step. So this is called using momentum. And of course, like these days, we have lot of variations of this, how you can use momentum. This is just a vanilla version of that. So this is just to give you a flavor of like how, what momentum means when you are trying to do learning using gradient descent. Okay, so now let's try to understand how this learning rate will affect like how fast your network will converge or whether it will converge or not. So if you use like a very small learning rate, then what's going to happen is, if you look at this equation, you will take very, very small steps, right? It will control like the gradient value. So then it's going to go very slow, like in very, very small steps. So it will take a lot of time. So if you increase the learning rate, so this is a curve showing like how it will affect, right? So these steps like is going to be controlled by this learning rate. Now, if you increase your learning rate, then what may happen, you might overshoot like your minima, right? If let's say you're using, if starting from this point to this point, it's let's say 10 units. If you use a learning rate of 20, then this is going to jump like from this location to this location, right? And then again, it will go away. So if you use like a very high learning rate, and again, this is showing the loss curve, which we discussed in the previous slide. X-axis is like the iteration or epoch as you're training your network. Y-axis is showing the loss value. Let's say this is the starting point, which was a random initialization. And these are showing like different variations of how your training loss will look like, or how your network will converge if you train using gradient descent. Okay. So the yellow curve, if you look at this kind of curve you will see when your learning rate is too high. Okay, so what's happening here is you're starting from this point and it's actually going close, but it will just cross this value. It won't go to this point because the learning rate is too high. And it will just keep jumping and eventually it will go out. So your loss is actually increasing. Okay, because it will rise like this level after some time. Then let's look at the other extreme, which is low learning rate. In this case, it will move very slowly, but eventually it will come to this point, right? So you can see like this is like the loss is reducing very gradually, but eventually it's going in that direction. Okay, so the other is the green one. And again, this is kind of a high learning rate, because what's happening here is it converges pretty fast, but then stays there. It's not moving at all. And the idea is, let's say you start from this location, you come to this point, then let's say you come to this point, then you just keep jumping here. So your loss is actually never going down because the learning rate is too high. It doesn't know how to take smaller steps. It will just keep jumping here. And that's the stagnant point here. Okay. And red is something which is like the optimal learning rate. It's increasing fast and then it's actually converging to a point. And again, these are all hypothetical scenarios. In real training, you will see like curves which I showed you in the previous slide, right? That's like more realistic, but this is a general trend which you should look for. Okay, so that was about learning curve. That will be useful for you when you train your networks. And as we discussed earlier, you have like certain set of hyperparameters in your network, and one of them is learning rate, which is very, very important. So by visualizing or analyzing those these loss curves, it tells you like whether your learning rate is correct or not, and that helps you set that hyperparameter to some extent. Now let's move on to the problem of fitting. Okay, so fitting is something your network has some set of parameters, right? So essentially, what's happening? It's a function, right? And when you're saying that your input is an image and you're making some predictions, so basically you're trying to learn some function which is performing this transformation from image domain to prediction domain. So essentially, it's a function, and that function is something which you are going to learn when you are training a network. Now, fitting is something when you take your data, so those parameters will make the transformations, right? So a perfect fit is something when you have those weight values which takes those input and make a perfect prediction without any error. Okay. Now, if you have too many parameters, then it will be very easy for your network to actually make those predictions, and that's called overfitting. I will describe that in more detail to be to make it more clear. So the idea is, if you have too many parameters, it will be easy for you to learn that function. You can easily approximate that, right? And that scenario is overfitting. That's not a good idea to do that. We'll talk about that why. The other extreme is you don't have enough parameters. For example, if you just use one neuron to approximate a very complex function, that's not possible, right? One neuron doesn't have that amount of capability. So in that case, it's called underfitting. It means that you are not able to approximate your function well. Now let's try to visualize like how these overfitting and underfitting looks like. So the other point is, if you use a lot of data, because your gradient steps or that learning process being performed on a lot of samples, which will have a lot of variations. So that actually helps you to avoid this overfitting scenario, even if you're using a lot of parameters. And that's one of the reasons why you need a lot of samples to train your networks. Because if you don't do that, your network will easily overfit. Okay, so let's first look at the loss curve and how we can relate like this loss curve with this overfitting problem. Now, again, this is the same loss curve. X-axis is like the training iterations or a number of epochs. This is just showing the loss value. That's the starting point. Now, the blue plot is the loss coming from the training samples. So the samples which are using to actually update your weights. All right. And then we talked about you had like two other splits. One is called validation and the other is called testing. Testing is something which you never look at. So testing, you just evaluate your model. Okay. But validation is something which you can actually peek through. You can test your model in validation and make corrections to your model. So what you will do is, as you are training your model, you will keep computing loss for the validation as well as the test set. Right? And this loss is actually computed over all the samples in the validation and all the samples in the test. So you can see initially all of three are like the loss is very high, which means the network is bad. But if you keep updating the network weights, you can see like the training loss is actually reducing, which should happen because you're using this loss to actually update those parameters, right? And you're moving in that direction, which will reduce the loss value. So ideally, your training loss should always go down unless your hyperparameters are not correct. Now, if you look carefully at like at these two curves, which are coming from validation and testing, you can see like until some point, they're actually following the same trend, which is reasonable because all the images or all the samples from validation and testing were never seen by this model. Okay. So it should be almost similar for both the sets. And at some point you can see like the loss is actually increasing. Okay, and you know that like the best model is something like where your loss is minimal. And again, that's questionable. There are variations to that as well. But let's just assume for now that okay, the lower the loss, the best the model is. So at this point, you can see if you keep training your model, the training loss is further going down, but your testing and your validation loss is actually increasing, which means your model is actually beginning to perform worse on your testing samples, which is not good because eventually you want to test a model on unseen samples, right? So this scenario is not good. And one way to interpret this is after this point onwards, the network is actually just trying to overfit on the training samples. It's just trying to learn those samples, or it's just trying to minimize the loss value specifically for those samples. So it's not like a generalized learning, because that learning is not being generalized to the testing samples. The loss is increasing there. So usually what we do is if we see such a point, we say that, okay, this is a point which is like the best network, and you use those weights as model prediction, even though your training loss is actually going down. So we don't care too much about the training loss. We care about the testing and validation loss. Okay, so this is the point when your network starts to overfit. And to avoid this overfitting, we have like different regularization techniques to use. So if you think about, just go back to neural networks and try to understand what this overfitting is. So neural networks, you have the input, you have the weights, you have those edges, right? And those weights are being used to actually transform the input values. Now, if some of your weights are actually too high, if they have very large value, then since the output is nothing but a linear combination using those weights, if one of the weight is too high, then that weight is actually dominating the output. It will control what the output is going to be. Okay. For example, let's say you have 3 different weights, and those weights have value 100, 1, and 1. And then you take the input, you take the linear combination, and let's say your input was again a 3-dimensional vector, which is again has value 1, 1, and 1. So if you take the linear combination, you can see that your output is going to be 102. Now, in whatever way you're going to use that activation 102 in the future layers, you can see that that 102 is controlled by the weight which has value 100. And most likely the other two weights are, they don't care, right? So if it's 102, it's 101, or almost similar, right? So that's like one way, like when how your network overfits, it tries to learn those kind of weights, which controls the predictions. So to avoid that, what we can do is we can add regularization, and a simple regularization is you try to minimize the values of your weights. You don't allow your values to be like some random numbers. Okay. So before going to like the regularization technique, let's try to first visualize what this data fitting problem is by looking at very, very simple examples. But again, whatever we are discussing, these are simple functions, but you can easily generalize these to complex functions such as neural networks. Now, these dots are your training samples. Okay, so in this case, the training data is just like 2-dimensional coordinates. Okay, so this is the training sample. Now, we want to learn a function which can make predictions about these points. Okay, so as a human being, it's easy for me. I mean, I can see that it seems like it could be like it could be a straight line, right, going from this direction to this direction. And the function which we learn could be a straight line, right, or something like this, or it could be a complex function, something like this, which is trying to go through each and every training sample. Right, so these are 2 different functions which, let's say, were learned. Now, if you try to compare the number of parameters in these functions, and again, that relates to like the number of parameters you have in your neural networks. In this case, it's just first order polynomial. Okay, so you don't need like, you need just 2 values. You need the slope of this curve and the intercept. So it's like 2 parameters to define this function. You can say this neural network, if it is a neural network. In this case, it's like a ninth order polynomial. So you need like that many parameters, right? That will be a very complex equation. But whatever that equation is, it's actually pretty good because it's going through each of these training points. Now, if you try to compute loss of this learned functions, in this case, definitely the loss is not going to be zero because this is the ground truth. But if you look the network's prediction, it's saying something like this. So there is some difference, right? The small difference between what the ground truth is and what your function learns. And that's true for like most of these points. And they're close to the line, but not completely over the line. So the loss will have some small amount of value. All right. But if you look at this function, which was again learned, a lot of parameters, and it's going through each point, the loss is going to be perfectly zero. Because this curve is actually able to predict each of these training samples pretty accurately. All of these points are lying on this curve. Okay, so this scenario is called overfitting. That's what happens if you pay attention to each and every sample of your training data. And if you have enough, like if you have sufficient amount of parameters, you will be able to do that. So this is called overfitting. And this is, I will say, kind of a perfect fit. This is something what we want. So, okay, so this is like, let's try to understand that from a binary classification point of view. So in this binary classification, we have two different classes, red and blue. All right. And all these dots are actually your training samples, again, shown on two-dimensional space. And these curves here are the functions which you're trying to learn. So in this case, this is underfitting, this is overfitting, and this is just like about right on a perfect fitting. Not a perfect fitting, but it's a good fitting. That's what we want. Now, if you try to analyze this, this is a straight line again, very few parameters, one or two parameters, right? So you have, it doesn't have the capability to learn like this complex boundary, because what we want is, we want a function which can divide like the red samples from the blue samples. Okay, so it will be curved like this, something like this. So this curve will have slightly more parameters than the straight line. Now, this is something overfitting because what it's trying to do is, it's trying to satisfy the loss function for each and every sample in your training data. It's making no mistake. So for training set, the loss is completely zero because all the red points are above this curve and all the blue points are below this curve. So loss is perfectly zero. In this case, again, you will have some loss. In this case, you will have a huge amount of loss because you are making errors for a lot of the samples. Red are like below the curve, right? And some blue are on top of this curve. In this case, again, it's not perfect because you can see like some blue dots on top and some red dots on the bottom, right? But if you think about, if you were given like some testing samples, okay, so this kind of function or this kind of curve will actually give you a more reasonable result as compared to this plot, which is overfitting, or this plot, which is kind of underfitting. Okay, so let's try to understand. So this is pretty clear. I mean, it's not working, right? Even for these samples, it's actually failing. So if it's not working for training sample, it's not going to work for testing sample. So let's go through the third one, which is overfitting, because it's working so perfectly on training sample. Now, let's say if you have a red dot, which is at this location, right where my laser pointer is. So it seems like it's coming from the red distribution, right? Because it's close to all of those. But this kind of curve will say, okay, no, it's a blue dot, and the method will fail. So that's why it's not good, because it's trying to, like, you can say, please each and every training samples, which is not good. In this case, you can clearly see the distribution. If you pick any red point like on top of this curve, it's going to be red. And if you pick any point towards the blue, it's going to be blue. The challenging cases will be like the boundary cases, but which is fine. That's like challenging even for humans. Okay, so that's what underfitting and overfitting means. And you should also be now able to understand like how number of parameters actually relates to underfitting and overfitting. Okay, so one easy solution for this is early stopping, which we discussed earlier. You just monitor your loss curve. And if your network is diverging, like for your training samples, so diverging is something when your loss started to like increase. That's called the divergence point. So you can use early stopping, just stop there and use that model. You can use regularization, which means like you try to minimize the weight values. Even in this case, when you will have some weights pretty high, right? That's why you're able to form these like complex curves here. So you try to minimize those weights. That's one way. You can use dropout. We'll briefly talk about that. And there are many other ways to avoid these problems. Okay. So we won't cover like all of those. So early stopping, we discussed whenever your network is diverging, the validation loss is increasing, you stop there. So that's called early stopping. Now, regularization is something where you try to penalize your network. So this is kind of an additional loss term you add. And what you want is you want to have small values for these weights. So what you can do is you can define like a very simple loss term, which is also called like a regularization term, which will ensure like your values for the weights is actually very small. So again, this is showing a simple example. So blue curve is overfitting, green is underfitting. And you can see that this, if this is a testing sample, the blue one is completely failing, but the green one is doing good job. Okay, so what we do is, if this is your standard loss function, which is taking data as input, these are network weights, and this function is like the network, which will give you some prediction. You will compare that prediction with the ground truth, and that's like your loss value. And this is your regularization term. You have a parameter here, which controls like how much importance you want to give to this regularization. Okay, again, this is a hyperparameter, and you use like the weights of your network as input. Okay, and this is also called a weight decay. And there are different variations of like of this regularization function you can use. You can use L1 norm, which is nothing but you compute L1 norm for each of your weights in the network. Just take the positive absolute value of that, right? And you just minimize that. So it will make sure that you don't have high values for weight, because if you have high value for weights, your loss value will increase. Okay, so you're trying to minimize these. And I think this also covers, like, I think when we're talking about basics of linear algebra, some of you asked like, what is the application of L1 norm, or in fact, like, what is the application of norm? So this is a very interesting application of those norm values. It doesn't have to be L1 norm. You can also use L2 norm. You can just square those values and try to minimize those. And there are a lot of other variations, but everywhere like the motivation is same. You don't want these weight values to be too high, because if you do that, then those weights will actually control what kind of prediction network is going to make. So, and you don't want that. You don't want to control the output of a network by just like some of those weights, right? You want to make use of all the weights to be able to make like a reasonable prediction. The other interesting idea to regularize your network is just use ensemble. Okay, so what does this mean? Because what you're doing is each time you're training your network, you are initializing your weights randomly. And you know that the loss function you have, it's not convex. So there could be like a lot of different minimas. And if you have different initialization of your networks, like when you do that like multiple times, which means that even if you train the same network multiple times, the final weights is going to be different because the initial weights was different, right? And if that is so, then what you can do is at the end, you can, let's say, train 10 different models and then come up with a way to like fuse those predictions. You can take average, or you can take, okay, the maximum number of predictions when, let's say, 5 of the network are saying it's a cat, then you say, okay, it's a cat. So there are different variations how you do that fusion. But the idea is making use of multiple networks. And again, these are not different networks, same networks. The only difference is the initial weights were different. Okay, so this is again, it acts as a very good regularizer, and it in most practical scenarios mean this is what it's used. So we don't just use single model, we use multiple models. Okay. Now another interesting thing is we initialize the weights randomly, and we want the value of the weights to be different. The reason is, if all the weights are actually equal, so what will happen, your network will not train, because you can think about this like all the values in your filters are same. right? So if you have 100 different filters, all the filters are going to give you same output, right? So when you compute the gradient at the end after you have the loss, so the gradient will be same for all the weights, right? Because the initial values were same, the outputs were same, nothing will be different, and the gradient will not change. The gradient will be same for all the weights. And when you make the update, again, the values will be same. So the network will not train at all. Okay, that's just a small point. Okay, so that's what I said. I mean, you don't just train one, you can train multiple models and just combine like those scores together. That helps you avoid this overfitting, and it also improves the performance. Another interesting aspect is dropout, and this is very interesting. So what you do is when you're training your network, let's say you have 100,000 different parameters or 100,000 different neurons, you don't utilize all of those at once. You just randomly switch off some of the neurons. Okay, for example, if this is your neural network, these are your neurons, you actually switch off these neurons. And as you pass your input in the feed forward, you will just ignore these. You will only use like the rest of the neurons to make the prediction. Now, what is happening is if you switch this off, then whatever loss value you have and the backpropagation, this neuron is actually independent of this neuron. It won't rely on this neuron. It will have to improve by itself. Okay, so that's called co-adaptation. And what will happen then, every epoch or every iteration, you change this. So next time what may happen, this is switched off and this is turned on. So again, this neuron will try to learn irrespective of what is the learning of this neuron. And since this is done like stochastically in a random fashion, so these neurons will never co-adapt to each other. Okay, so you can think about this. Let's say you are working on a course project, right? A group project, and you have a group of 10 students. So what may happen is you might have one student in the group or multiple students in the group who are actually relying on other students. So they won't do anything. What they will do is whatever other students are doing, they will just copy it or do something which is based on what other neurons are doing. So essentially, then those students are not learning at all. And at the end, what will happen is whatever outcome you have from that project, so the good students who are actually learning, that will be used. But those students who are just trying to copy the other students, they are kind of useless because you don't need them, right? Even if you don't have those students, your outcome is not going to change. Now, what we are doing is we are shutting off like those students randomly. Then if one student is actually relying on other student, if that student is not present in one of the class, then the student will have to learn. Otherwise, this student can't minimize its loss, right? But it will not produce like good predictions or good outputs. So then it will have to learn. And again, it can try to co-adapt to other students, but again, in some of the other classes, those students will be absent. So that's like a general intuition how this dropout works. And again, this also helps you in like reducing the overfitting issue. Okay, so these units are useful independently, and ideally, like you set this to 0.5, which means that you turn off like 50% of the neurons. And sometimes this is too high. I mean, sometimes you do like 5% or 10%. That again depends upon what kind of architecture you have and what kind of data you have. Okay, so those were like different key aspects which I wanted to discuss. Now let's follow like the training steps. So what you do is you have the problem, you know what problem to solve. So you know like what will be your network's input and what's going to be the output. And depending upon that, you will first define your network. Okay, so you will be the architecture of the network. You will define how many layers you want, how many kernels you want to use, what should be the shape, all those hyperparameters you will define. So that will give you the network. Then you know that what your network is going to predict, and then you know that what kind of ground truth is available. So using those two values, you will define a loss function. Okay. For example, if we are doing classification, you can use binary cross entropy. We discussed that loss function last time. Of course, that's not the only loss function you can use. That's the most like common one, and it usually works pretty well. Then you will randomly initialize the network parameters. For example, if you have CNN layers, you will randomly initialize those kernels. Okay, so those kernels will have some value. Then you will have the training data. And with that training data, the steps which we discussed earlier, you will randomly shuffle it. You want it to be like stochastic. And then you will prepare batches, like the number of samples which you will use to train your network, like for one iteration. Okay. So once you have the batch, you will perform that feed forward operation, which is like you will take each sample and you will run it through the network, which means like you are performing all those transformations, all those filtering operations. So it's going from volume to volume all the way until the final prediction. So for each sample, you will predict something. And within a batch, you will do, let's say your batch size is 16, you will do that for all the 16 samples. And so now what will happen? You will have 16 different predictions for the network, and you will have corresponding ground truths as well. So using your loss function, then you will compute the loss value, like how good your network is doing on those samples. Okay, we'll compute the loss. And then the next step is computing the gradients. So you have the loss function, you will compute the partial derivative for that loss function to all the, with respect to all the parameters. So we'll start from the final layer and you will use the chain rule to move to the initial layers. So for each parameter in the network, then you will have the gradient value. So that's called like a backpropagation, or you can say like gradient computation. So once you have the gradient value, you know that step from gradient descent, right? So we'll perform that step for each and every parameter in your network. And that's called like updating the network parameters, and that completes your training process for one iteration. Okay, so you repeat for all the batches. That completes one epoch, which means your network has seen all the samples in your training data. And then you keep repeating that to make your network better and better. Okay, so the loss is going to reduce in each epoch. Okay, so that's like the general idea of training. And again, we'll talk about this like in more detail when we talk about the data loader and when we cover the PyTorch tutorial for you, right? So that's the next lecture. Now let's try to understand like what different parameters we just covered, and let's connect that with the LXNet architecture. Okay, so all these hyperparameters, or you can say like the network design parameters, we already know. We know like the shape of the image, we know like all these kernel sizes, how many kernels we are using. So that was one aspect. Okay, so that gives you the network. Now to be able to train it, what you need is, for example, like what activation. So we are using ReLU activation in this LXNet. And then the dropout is 0.5. You know what dropout is. Batch size was 128. Again, these are the parameters which were used by like that first work which started this deep learning revolution. Okay. And of course, these were like determined empirically. And again, it's not that these are the perfect values which you should follow. It will change with like the data set you're using, with the network you're using. But these are some set of hyperparameters which are used by those researchers. Okay, so they used a batch size of 128, which means like in one batch, there will be 128 images when you compute the loss value and compute the gradients and perform the network of weight update. Okay, so SGD was used. That's like the algorithm we discussed. Momentum was 0.9. Again, we discussed what momentum means. Learning rate was 0.01. Again, you know what learning rate is. That defines like what will be the step size when you make those gradient updates. And the decay for learning rate was like reduced by 10 manually after like the validation accuracy plateaus. What this means is you observe like the validation loss, or you can say accuracy. And if it's not changing, they were reducing like the learning rate by this amount. So the idea here is, as you go closer to your local optima, you don't want to just keep jumping around that point, right? You want to go to that point. So if that is happening, which is like this accuracy plateaus, right? Your loss will not change, your accuracy will not change. Then you reduce the learning rate. Then you start taking like smaller steps. Okay. So then L2 weight decay was this. This is again the regularization term we discussed. So this is like a value for that. And this is again, we will continue the lecture on training neural networks from last week. And so this is the last segment of this lecture. We have already covered what are the different components in the training process and what the training process actually looks like. So the last segment is we will just try to cover different variants of convolutional neural networks and the motivation why like those architecture were designed. And this is by no means like a very comprehensive list. This is some of the variants. And of course, there are like a lot of other variants out there. And I mean, these variants are being developed like very, very rapidly, right? So for example, these days we have transformers model and everyone is now like focusing just on transformers. So most of the recent neural networks you will see, even for images and videos, they are based on transformers. So in a way, you can say like the architectures which we are going to study, they are already outdated. The fact is like these were developed like few years back. And so you can see that like how fast, how rapid the field is moving. So things are changing very, very fast. Okay, so the first architecture we are going to discuss is residual network. And the idea here is we know how to construct a convolutional neural network, right? Or a neural network in general. And you know how that model is actually trained. So during training, you have two steps. The first is you take your sample, you do a forward pass. All right. So whatever weights you have, those weights will perform the transformations. They will take the input image, they will create activations. And as you move on deeper into the network, you will get like those sequential activations. And at the end, the model is going to give you predictions. Okay, so that's how it works. So that's a forward pass. Then the actual training process is the backward pass, which is done using backpropagation, which we studied in the last lecture. And backpropagation is depending upon the network's prediction, you compute some loss, you compute the gradients for each parameter in your network. And depending upon that gradient, you update the weights. So that's kind of, you are moving from the last layer of the network to the first layer. So that's the backward pass, and that's the actual training. All right. So now the issue is, if your networks are too deep, then what will happen is when you compute the derivative, you might have some loss value. Okay. So the some of the final layers, you can use that like a loss function, you compute the derivative. But since this is based on chain rule, and chain rule you have seen that's kind of multiplicative operation, right? So if your loss is very small and your derivative is also very small, then what will happen is if you keep using the chain rule and keep like computing the derivatives for your parameters, which are like, let's say, some of the initial layers of the network, then those values will be very small because of the chain rule, which is, as I said, it's multiplicative, right? If you multiply two small values, you will get smaller values. Okay, and again, depending upon if it's less than 1 or greater than 1. And those are the two different aspects of this. So the issue is, if your loss is or gradients are very small at the end, as you move to the initial part of the network, they will kind of diminish close to 0, and the initial layers will not be trained. Okay, so that's one extreme. The other extreme is if your loss is too high or your gradients are too high, for example, like values greater than 1. And in that case, like the final layers, you will get some gradient, you can update. But again, since the chain rule is multiplicative, if you try to compute gradients for the initial layers, due to the multiplicative nature, the magnitude of that gradient is going to explode, right? And as you reach like the initial layers, you will update like the weights with a very, very big numbers. And again, that's the other extreme. So we want something in between. Okay. So that's the issue with like deep networks. And one of the reasons why it's very hard to train, like when you have very, very deep networks. Okay. So that issue is called, you can say, vanishing gradient. As you move to the initial layers, your gradient is actually vanishing, or you can say gradient explosion. Now, to resolve that issue, this kind of residual connection was proposed, and whenever you use this kind of residual connection, we call this like usually for CNNs, this is called like a ResNet network. Okay? And there are a lot of variants, but the basic idea remains the same. You have a shortcut connection from one of the initial layers to the later part of your network. All right, so what's happening here? This is your data flow. It could be image or maybe some activations in your network. And let's say this is like some kind of CNN layer. You have the activation against some CNN layer activation. Now what you're doing is you're actually adding this skip connection. So this data is actually flowing through this path as well. And you're adding that value to this activation over here. So this is the exact function. If you define these two layers in form of a function, which is fx here, then the output after this layer will be fx plus x, because you're adding the activation which was generated after this layer to the value which was at this point of time. Okay, so this is called skip connection, and you can also call this like a residual connection, because you are flowing like your values. You're kind of shortcutting the connections here. Now let's try to understand why this is useful. Now, as we discussed, the issue was like your gradients were vanishing or they were exploding, right? Now, what will happen in this particular case if your gradients are always flowing in the backward direction, right? It's the back propagation. So whatever gradient you have at this point of time, then we covered this part. Whenever you have an addition operation, you just distribute that gradient, right? So the gradient will go in this direction, and the gradient will also go in this direction. So because of this shortcut connection, what's going to happen is whatever gradient you have at this point of time, it will be reached here, and this point will also receive gradient from this branch. So the gradient is actually coming from two different directions. Now, even if like the gradient is actually becoming very small here, but you still keep this gradient, which was not actually small, right? So this shortcut actually ensures the gradient value is not close to zero. It will have some magnitude. Okay, and then the issue of like vanishing gradient is actually resolved. So it doesn't matter like how deep your networks are. The skip connection will make sure you have gradients ready, like, or some meaningful gradients for the initial layers as well. So the question is like how to add these skip connections. And again, there are a lot of variations. You can actually have skip connection surrounding each layer as well, or some group of layers as well. Okay, so all those can be variations, but the motivation remains the same. Okay, so then this is, as we discussed, it's actually helping you in backpropagation. So whenever you will see like a model architecture which is based on ResNet, then you have these kind of residual connections in those architectures. So this is like one category of CNNs. Now we have another category which is called inception. So these are called like inception net. You can say, or maybe Google Net, because they were developed by Google. Now, the motivation for ResNet was to be able to train deeper networks. Okay, inception is like slightly different. In this case, of course, these networks are also deeper, but this one is more focused towards creating like wider networks. Okay, let me try to explain what wider means here. In a normal CNN, what you do is you take your activation and you have like some set of filters. So it's just like a single branch going forward. And you decide on like what will be your kernel size. It could be 3x3 or 5x5. Whatever that size is, you use it and you move forward. Now, the motivation here is it's actually making wider, but let's try to understand the intuition there. In your input image, you might have different scales, right? So you might have something like, let me try to, okay. So you might have, let's say you're detecting shapes, you're detecting square objects, right? So you might have an image where this is the square and you're trying to detect this. You might have another image of square of a different scale, this small. Or you might have a different image of slightly bigger size, right? Now, what will happen if your kernel size is fixed, let's say 3x3, its receptive field will be like fixed. So if you change the aspect ratio, or not the aspect ratio, if you change the resolution of your input image, then your output will change because the receptive field remains fixed, right? It's just looking at 3x3 window. So that's the motivation. We want it to be like scale invariant. So what we do, we have different shape kernels. So in this case, we are using 3x3. We can also use 5x5. So in this case, even if it's bigger, then 5x5 kernel will take care of that. And we can have 7x7 as well. Okay, so we are actually looking at different resolutions at the same level of the layer. And that's why like these layers are getting thicker. Okay, and this is just one sample. Of course, you can have a lot of different variations here. So you are just looking at the pixel location, which is 1x1. So idea here is you don't really care about the neighbors. You only care about like what different feature sets you have across the channels. And whatever inference you're making, you're just trying to compute the linear combination of those activations, right? And this is 3x3, so this is trying to look at like a local neighborhood as well. 5x5, slightly bigger neighborhood. And again, this is trying to do a max pooling. So you first reduce the shape and then again you just look at. So these are different variations. And you do all of these in the single layer. Okay, so as I said, the ResNets were trying to focus on deeper networks, and InceptionNet is trying to actually create wider networks to be able to invariant to like those scale changes. Okay, so this kind of architectures, it's more efficient as well. Now, another category is DenseNet. And this is actually, you can say extension of ResNet, but like in a more aggressive way. Okay, so what it's trying to do is, it's not just trying to create skip connections like at some of the places, it's trying to make these connections like in all the possible ways. And the idea is you create like these group of convolutions. So if this is 4, it means like you have 4 different convolution layers. And what you do is you pass on the output of this dense block to all the future activations, right? These green lines. Similarly, like if you look at this red one, red block here, this activation is actually going to all the future blocks. And how you pass them, you just concatenate, or you can add as well. It's up to you, right? It's just like you are looking at like these different level of feature activations at all the possible layers. Okay, then this is like just one dense block, and then what you do, you have like sequence of these dense blocks. Okay, so this is again just a variant of ResNet, and of course it performs better than ResNet because you have like these like dense connections, which makes it it improves the learning power of the model.